this class we will discuss something called shock polar related to oblique shocks, and we will draw the velocity triangles again. Oblique shocks. Let us start with the velocity triangle. So, if this is a shock, I have V1 approaching the shock, there is a tangent, then there is a velocity component normal to the shock, then after the shock we have the velocity V2n deflected. V1 is deflected by some angle, and the tangent Vt we have seen to be same as V1t. So, V2t is same as V1t. So, I use Vt as the notation for V tangent. So, this is my V2, this is theta, this is beta minus theta, and this is the shock angle beta. Okay. So, this is for a scenario where we have something like this. So, I have a shock and this is theta and this is beta. So, V1 comes deflected to V2. Okay. Now, I am going to draw this velocity triangle in the following way. So, I have Vt, V1 and normal to Vt is my V1n. So, I have V1, V1n and V tangent. So, this is my beta. So, this V1 is deflected at theta degrees somewhere here. So, this would be my V2 and this distance is my V2n. So, all I have done is I have drawn these two plots together in this particular case. So, this would be my theta. Okay. Fine. So, this is my V1n, this is my V2n. Now, what I am going to draw is I am going to plot these components in xy plane, where my x axis represent Vx and y axis represent Vy. So, Vy is x component of velocity, Vy is the y component of velocity. Okay. Whether it is 1 or 2, it is different. Now, suffix n is normal to the shock, t is tangential to the shock. Okay. That is a nomenclature we have used for the oblique shock. Now, I will take V1 along the x direction. So, I am going to plot this thing with the direction V1 along the x direction. Okay. So, I have V1 here, okay, which is also your V1x Then I have a component here. This is my V tangent and V1n. Okay, and this would be my beta. So, for V1 is V1x, which means V1y is 0. There is no component of V1 along the y direction. Now, because of the oblique shock, there will be a deflection of your velocity, which is V2, which produce a normal component V2n, which are the same tangential component, normal and tangential to the shock. So, this V2 has a component V2x and component V2y. Okay. Now, I am going to draw the same plot without those details, just V1 and V2. Okay. So, I have V1 and a V2. Okay. All these components are assumed to be present there too. Okay. So, without these details, just this vector and this vector is what I have drawn here. Okay. So, this is for a given beta and theta. For some Mach number, for a given theta, this is what I do. So, what does it mean? So, I have a plot like this, I have a ramp like this with some value of theta. There is a V1 coming, it hits the oblique shock, then take a turn, is V2. Okay. Now, if I keep changing my theta, okay, this point increase or decrease as I increase or decrease my theta, and we also have seen there is a theta max associated with this. Okay, for a given Mach number, for a given m1, there is a theta max. So, there is a limit to which you can increase or decrease, so that you have a solution from our theta beta relation, which is your tan theta is 2 cot beta m1 square sin square beta minus 1 divided by m1 square gamma plus cos 2 beta plus 2. Okay. So, I am going to increase my theta and I would get a different value of this point. If I decrease it, I would get a different value here, and if I connect all these dots, this would become something like this, where this is my theta max. Okay. So, all I have done is I have changed my theta to get this particular point, and for different values of theta I would get a locus something similar to this. So, that I would draw it with a red line. Okay. This is the so called autograph. which is nothing but the locus of points related to the velocity, that is before and after the shock. So, if I know the autograph, something like this, I will draw a smaller curve. So, I have at some point I have for some value of theta, I have V2 from the V1. V1 is kept constant. So, for this particular value of theta, I have a different value of V2. So, if I connect this line, and the perpendicular to this to the axis. So, if I get a perpendicular to this particular line to the axis, that would give me the shock angle. So, compare this with the velocity triangle that we have drawn here, this is what you would see there. So, the point connecting V1 and V2 and extend that, the normal from there to the origin should give me the V tangential, and the angle between that and Vt should be your beta, which is what you would see here. Okay. Now, what I am going to do is, I would divide, so this is my Vy, I am going to divide this by A star and this by A star. Okay. So, all I am going to take, I will take this particular curve and divide it by A star and A star. Okay. So, I will rub these plots. Remember, this is not after the shock, this is the x component of the velocity and the star associated. So, it is not mx star as we see it in the normal shock, and this is not the my star after the shock. This is the component of velocity in the x and y direction. Okay. So, probably I should I would leave it as it is instead of using the Mach number relation. Okay. So, if I get this plot, this is again the velocity divided by A star, V2 divided by A star. So, that would be my M2 star. Okay. So, this particular line is for a given V1 or M1. Okay. And the tangent would give me the theta max, and somewhere here is the point where I would get my M star equals 1. So, M2 star equals 1, which is also your M2. So, that is what you would see in your theta beta relation, theta theta for a given M1. This is my theta max. For some combination of theta and beta, I would have my M2 equals 1. So, this line would give me that particular demarcation which gives me a strong shock and a weak shock, and this is the so called sonic line that we have already seen in theta beta m relation. Okay. So, this point is what I have written here as dot, and this is the theta max plot. So, I would put this red dot as my sonic line and this as the theta max. So, there are two different points as we have already seen in the theta beta m chart. And remember, this is for a given Mach number, given m1, okay. And this is the so called shock polar diagram, okay. So, if I know the Mach number based on my velocity components x and y, I can draw this and find the solutions where I get theta max and m2, the sonic condition. So, this is for a given m, and for other m's you would get plots similar to this, and you can find the locus of all these points which gives m2 equals 1. So, that is your sonic line corresponding to what you have seen here in the theta beta m relation, okay. And this point on the x axis, these 2 points on the x axis gives me theta equals 0, which is precisely these 2 points for a some value of your m1, okay. So, there is no deflection of your velocity vector v1 if your theta is if your beta is this or this, which is this 2 values, which is this normal shock pi by 2 or your Mach angle mu. For these 2 values, there is no deflection of your velocity vector, which means theta equals 0, which are the points that is lying on your x axis. So, for other values of Mach numbers, you would get something like this, and this is what you call as the shock polar, okay. Now, you could also get the equations for this, you can derive the equations for the shock polar. For that, first we will derive the Prandtl's relation for oblique shock, and then we will proceed to this. So, for a normal shock we have seen Vx, Vy is Ax star square. Now, for an oblique shock, this would be modified to something which is the following, okay. So, this is what we will derive, and for which we will start from the continuity equation rho 1 V1 n equals rho 2 V2 n, and the momentum equation is this. Okay. This can be rearranged as no, first we will write the energy equation H1 plus V1 square n by 2 equals H2 plus V2n square by 2, which I will rewrite as V1 square by 2 plus gamma by gamma minus 1 into P1 rho 1 is V2 square by 2 plus rho minus 1 P2 by rho 2, which is for a normal shock. Or just simply the energy equation between 2 points V1 1 and 2, okay, which we can relate it to the stagnation condition, which is Cp T0 into R T0. Okay, so this is your stagnation the total temperature that is given from the energy equation. Okay. So, which we also know T0 by T star is gamma plus 1 by 2, and your A star is nothing but gamma R T star. A star square is gamma R T star. So, I am going to use these two relation to get T0 as A star square by gamma R into gamma plus 1 by 2. I just converted T star in terms of stagnation temperature, that is all I have done here. Okay. So, across the oblique shock the temperature, the stagnation temperature is constant. So, I can write like this. So, A star will also be a constant across the oblique shock. Okay. I am going to substitute this here in this equation. So, I will rewrite that as V1 square by 2 plus gamma by gamma minus 1 into P1 by rho 1 equals V2 square by 2 into gamma by gamma minus 1 into P2 by rho 2. Plus equals gamma by gamma minus 1 into R. Instead of T0 I would write this A star square divided by gamma R into gamma plus 1 by 2. So, this get me two relation P1 by rho 1 equals gamma plus 1 by 2 gamma A star square minus gamma minus 1 by 2 into V1 square by 2. Likewise, P2 by rho 2 is gamma plus 1 by 2 gamma A star square minus gamma minus 1 by 2 V square by 2 from this equation. So, I had split this equals into those two equations. So, when it comes to the oblique shock relation, all I need to substitute is instead of V2 I would substitute as V1n, instead of V1 I will substitute V1n and V2 is V2n. Okay. So, for oblique shock I will replace V1n with V2n with the normal component. Okay. And from momentum equation, which we have written as P1 minus P2 as rho 2 into V2 n square minus rho 1 into V1 n square. I would rewrite this as V1 n minus P2 by rho 2 V2 n equals V2 n minus V1 n. Okay. So, this is my equation 1, and this two equations I can get V2n minus V1n from this equation. Okay. So, my equations are P1 by rho 1 equals gamma plus 1 by 2 gamma A star square minus gamma minus 1 by 2 B1 square by 2 and P2 by rho 2 into gamma plus 1 by 2 gamma into A1 star minus gamma minus 1 by 2 V2 square by 2. Okay. So, now I am going to multiply this equation with divide by V1n and the second equation by V2n, so that I would get P1 divided by 1 by Vn A star square by 1 V1n minus gamma minus 1 by 2 V1 square by V1n. Okay. So, to get this particular form, so P1 by rho 1 I have divided it by V1n. So, this equation I have divided with 1 by Vn. Likewise, P2 by rho 2 into 1 by V2n is gamma plus 1 by 2 gamma A star square by V2n minus gamma minus 1 by 2 into V2 square by V2n. Okay. So, this is my A and this is my B. So, I divide subtract A minus B. So, I would get gamma plus 1 by 2 gamma A star square by V1n minus gamma minus 1 by 2 into V1 square by V1n divided by V2n. By V2n.
V1 square by 2 times V1n, V2 square by 2 times V2n. If you see the original equation is V1 square by 2.
Oh, okay. So, there will be 1 by 2 here. Okay, so there is a correction here. There is a 1 by 2 here, 1 by 2 here. So, this 1 by 2 is missing here. So, there would be a 1 by 2 here and gamma plus 1 by 2 gamma A star square by V2n minus So, we have subtracted this. So, which would be equals to P1 by rho 1 V1n minus P2 by rho 2 V2n, which we know from equation 1 as V2n minus V1n. Okay. So, we are substituting this value, this and this from the equation this we are seen is equal to V2n minus V1n, which is what I have written here. So, this can be modified if I do this. T square, and if I substitute this here, and we also know V1 V1t is same as V2t. So, I have just written Vt here. So, if I substitute that and do some simplification, I would end up with the relation that looks like the following: gamma plus 1 by 2 gamma into A star square V2n minus V1n divided by V1n V2n plus gamma minus 1 by 2 V2n minus V1n plus gamma minus 1 by 2 into Vt square by 2n minus Vt square by V1n equals V2n minus V1n. So, if I can take V2n outside from these quantities, I would get V1n into V2n equals A star square minus gamma minus 1 by 2 into Vt square. So, I divide this equation with V2n minus V1n. So, this cancels out, this cancels out, then the numerator here cancels out. So, I will end up with equation that is here. Okay, this is the this is gamma minus 1 by 2 by gamma plus 1, correct? This is gamma minus 1 by 2. So, that is the Prandtl relation for oblique shock. So, for normal shock Vt is 0. So, you would equation reduces to the normal shock form. V1n is V1, V2n is V2 and Vt is 0. So, this would reduce to V1 V2 equals A2 star. So, V1 is velocity before the shock, V2 is velocity after the shock is A star square. Okay. Now, we will use this relation to find the equation for the shock polar. Which is not very difficult. We will just draw that particular velocity diagram which we had just now drawn. So, I have a V1, then I have a V2, this is V2, this is theta, this would be my beta, this is Vt, this is Vn1, V1n, and this is V2 and this is my V1. Okay. So, this is beta. So, this will also be beta, and this component is your Vx2, V1 is same as my Vx1 or V1x. Okay. So, I can write V1n as Vx1 sin beta, V tangential is Vx1 into cos beta, and V2n is V1n minus root of Vy2 with this is Vy2 plus Vx1 minus Vx2 the whole square. Okay. So, the V2n is this. So, you can look at the triangle and get this relation. So, V2n is V1n, V1n is this much minus this length. Okay. So, V2n is V1n minus say let us say this has length A. So, that is minus A. So, this A is from this angle or from this triangle you can get this length, and that length is what is written here. This height is V2x, Vy2, and this is this whole length minus this. Okay. So, this is my Vx2 and this whole length is V1 which is Vx1. So, this length is my length B. So, from this triangle which the height is Vy2 and this length is B, I can compute this particular length which is my A, and from if I know A, V1 minus A is my V2. Okay, that is all I have done here, which can be modified with the particular relation which is the Prandtl's relation V1 V2n equals A star square minus gamma minus 1 into gamma plus 1 into Vt square. So, you can substitute that relation, use that relation to get this equation which can be modified. V2n can be modified as V1n is Vx1 sin beta minus Vy2 square plus this quantity root. So, if we substitute all this, I would end up with a relation that is the following: Vy2 by V star square equals M1 minus Vx by A star the whole square into Vx by V star into M1 star minus 1. So, this is star divided by 2 by gamma plus 1 M1 star square minus Vx by Ax the m1 star plus 1. Okay. So, plus 1 plus 1. No, it's plus 1. Okay. So, for a given m1 star, for every Vx you can get a V2. The moment you get a V2, you can extend that for change your m1 and get this thing. So, in this plot, so how do we plot this? That particular equation. So, Vy2 is a function of m1 star and Vx, and of course gamma and A star. So, let us assume gamma and A star to be constant. This is a function of m1 star and Vx star. So, what we need is this particular plot. So, this is Vx by Ax star, Vy by A star. Okay. So, this point somewhere here is my Vy by A star. So, what we have is Vy. So, if I change for a given Vx, keep changing my m1, or for given m1 change these theta values, so that I would get the point here, which is the locus, which is what is given by this equation. Okay. So, this is your equation to your shock polar. Okay. So, in this class what we have done is the concept of shock polar and how we can plot the velocity components in the x and y direction and get some information about the flow directions and the shock waves. And if you have a theta greater than theta max, the solution does not exist for whatever we have done. So, it would be a detached shock or something, or a Bosch shock as it is called. So, all those condition comes out of this particular relation between theta, beta, m. Okay. Thank you.